Hello again, Machine Shop Math fans. This will be video number 8, if I'm not mistaken. Again, whatever the title on the file is. This is going to be dealing with some concepts of threads and threading. Now, as a precision riflesmith, someone who has spent a great deal of his life making long-range precision rifles for sport and for tactical use, and who has spent a lot of time in his many lives on this planet, from the Marine Corps through policing to engineering and rifle competition. The screw is a very important thing. Well, rifling in a barrel is a screw. Rifle barrels are screwed into an action. Many things in machining and industry are screwed. I am going to put some videos on D2L on how screws and bolts and nuts are made, so you understand how they're commercially done. If you cannot manually cut a screw on a manual lathe, then in my opinion you're not a machinist, and we'll just leave it at that. Alright, so the history of the screw. The history of the screw. So I get my cursor over here, and as always we're going to want to draw on this, and I'll use red unless somebody starts complaining about red. Alright, from the early historical times to the 20th century, screws have been around for a long time. Here's some examples. Here's some ancient jewelry. This is a Roman speculum. It was a medical device. Still use speculums today. Gynecologists use them. OBGYNs used to yank the babies out with a speculum. I don't think they use those anymore. But this was one from the Roman time of 50 AD. 50 AD. The word cesarean section comes from Caesar, from ancient Rome, where they would open up the belly of a pregnant woman who was having trouble getting the child through the birth canal, and they didn't have a lot of anesthesia back then. So imagine that was an interesting trip. And you can bite down on a leather piece of leather or stick or something. But anyway, here's Archimedes. Now Archimedes is he did a lot of work with screws. Archimedes is like Euclid. The Archimedean screw. Here's a screw pump right here. We use screw pumps still today. When I was a civil engineer, I installed and designed a lot of screw pumps for lifting large volumes of water over a short distance in height. The Texas City Dike used to have huge screw pumps to take the storm water from one side of the dike and throw it over into the bay. Read through this document, the history of the screw. It's interesting. Let's see here. It talks about Hercules and various. So the screw has been around a long time. The term screw is used for all kinds of stuff. You know, the term screw up something is to mess it up, or you need to screw it down, tighten it up, or just the common term for screw is an equation to coitus or something. So anyway, we'll be talking about the mechanical aspect of the screw. Here is a wine press that has a screw. The Spaniards and the Turks had an execution chair that used a screw that would strap your head to the chair and your body to the chair, and then they would take a giant screw and break your neck as you're sitting upright. I think one of the James Bond movies had that execution chair in it, and the movie The Original Sin with Banderas and Angelina Jolie. Anyway, I digress. So the screw's been around for a long, long time. The standard for screws you'll find in Machinery's Handbook. I'm not gonna do a lot of screwing math. Screwing math. Boy, that didn't sound good, did it? We'll be talking about leads of screws, and that'll be on the exam too. Other than that, you'll get the rest of your screw mathematics and how to read Machinery's Handbook in your machine shop classes, or you should. So we're going to get some basic vocabulary. Now, Whitworth was an engineer who designed the Whitworth screw in the 1803s and 1897, somewhere in this period here. You can blow this up and you'll see this is a trapezoidal thread, a taper thread, double start. A buttress thread is supposed to be self-locking like in a jack. Round thread, you see these, and ball screws in our CNC machines, and a square thread. There are all kinds of threads. Many manufacturers, NOV, Halliburton, they have proprietary threads. So we move on into the 20th century. Basically the fan turbine inside a jet engine essentially is a threading deal. A die plate for the protection of threads. This is ancient days of yore. Like I said, I'll be putting some videos up that you can watch on how things are made. I'll try to locate them. And here's a turning lathe that has a threading attachment, screw manufacturing attachment to them. Now let's go over here to identifying screw threads. Now, this was a large paper, and I didn't put it all up here. Here are some common thread forms. These are not all of them. You could spend your whole life being a threading engineer, threading specialist. Here's a worm screw, worm drive. It's like a 40-degree angle. A sub-acme is less than 30, so it's 29 degrees. An acme thread is 29 degrees. Here's a ball, full radius ball, like you might find in a CNC machine, or a linear motor. Here's an offset so that the ball doesn't make full contact. The ball would make full contact in here, and it would not in here. And this is the isometric tapered thread. Now these are just some. These are not all of them. What the ball threading does is it eliminates the backlash as much as we possibly can. So let's get into some terms. You got major diameter. The major diameter of an external thread. Now, an external thread in Machinery's Handbook, an external, is noted by the letter, oh my goodness, here, draw. Oh, that's right, we got to do this for each one of these. That's red, orange. We'll just do red. Okay. External thread is designated by an A thread. Now, this is ISO. This is not in metric land. This is A. So A is external, or a male thread. Or the male. It's easy enough. An external thread or a male thread is A, because it's exposed to the air. It's outside. You can see the threads. Okay, air. Okay. Here's the major diameter. It's measured from the top of the root. It's measured from the top of the threads, the crest of the threads. Okay. The top of that threading is called the crest. Down here's the root. Okay. Now, pitch diameter. When we're measuring threads, we really like to measure for the pitch diameter. I wonder if I can make this bigger. Let's see if we can make this bigger. Yeah, we can make it bigger. Let's make it bigger. All right, the pitch diameter is not the crest or the root. In other words, here's the root on an external thread. That would be the root. This would be the crest. The pitch diameter is an imaginary point halfway between. The pitch diameter is an imaginary point halfway between the crest and the root. And that's really what we're measuring. We're measuring the pitch diameter. And in Machinery's Handbook, when you get there in your machine shop classes, you'll see that the pitch diameter for an A thread will be a little different versus an internal thread, or B. Now, B for an internal thread, you can think of it as bore. It's thread inside a hole. So A is for air, external, and B is for bore, internal. Internal. Okay. All right. The minor diameter, the major diameter is measured at the crest. The minor diameter is measured at the root. And these all have pluses or minuses. We call it tolerance, based on the type of thread and whether it's a 2A or a 3A or a 1A thread. 1 is the loosest, 2 is your normal threading, and 3 would be your tightest tolerance of any of the threads, whether it's an A or a B thread. The hand of the thread, whether it's a right-hand thread or a left-hand thread. Okay, and this determines and easy to determine by visual inspection. Simply compare your screw threads with the right hand and left hand threads illustrated down here. Most threads are right hand, and right hand is assumed if no left hand designation is specified. Just like if I tell you to cut a thread and I don't tell you it's a 3A or a 1A, the assumption is it would be a 2A thread. And unless I tell you otherwise, it's also going to be a right hand. Now for my gun barrels, I am as tight as I can get. I want a 3A thread for the shank of that barrel. For the shank of the barrel. We'll have the bore through here. And so the threads along in here, I'm going to cut at a 3A to match the female thread I got to meet up to, which is the action, which has the threading in here. Okay. All right. The number of starts will dictate the number of starts of your thread will depend on if it's a 1 start, a 2 start, a 3 start, or a 4 start thread. And that will be on your next exam, exam number 2. And it'll be real simple. I'll give you the equation. So you need to read this. A 1 start thread is your normal thread. If you just go to a hardware store and you buy a bolt, it's going to be a single start. It will be a single start thread. It will be a single start thread. It will be a single start thread. Now we talked about the pitch diameter. The pitch diameter, the imaginary circle across here. The imaginary circle, halfway between the root and the deal. That's the pitch diameter. But the pitch of a thread is measured, it's the distance. Oh my God, that's horrible. Woo, that's terrible. The pitch is the distance between, good God, it's the distance between two of the crest. That's the pitch. That's with a P. That's the pitch. So, now if you go and you go to the hardware store, the guy working or the gal working at the hardware store, and say, well, what pitch do you want? Well, you're really not asking for pitch, you're asking for TPI, threads per inch. Threads per inch. And this is where people get this all mixed up, threads per inch. Now in metric land, we don't have inches, so metric threads are determined by the pitch, but in ISO land, you might want, I don't know, let's say a 3/8 by, I don't know, what would be a 3/8? We'll say a 14 TPI. TPI. Now, that doesn't mean that the distance across, that doesn't mean that the major diameter is 3/8 of an inch. That's the nominal. What that means is it's the nominal 3/8. It's really going to be less. You'd go into Machinery's Handbook and find what is the major, the max and min of the major diameter for a 3/8 to a thread. All right, but that's the nominal. The threads per inch is if we measured 1 inch along here. Let's say that was 1 inch. Then theoretically we would have 14 threads. 14 threads. Now there's a relationship for pitch. Pitch is 1 over the TPI. Now if this was a metric thread, and let's say it would be an M10, that means the nominal diameter is 10 millimeters, and then the next one might be, I don't know, let's say 1.05. That may not even exist in metric land, but let's just say it does. This is the pitch. This is the pitch. Whereas in this case, this is the TPI. You could spend a whole semester discussing threads and threading engineering and all that kind of stuff. All right. So, so if it was metric, it would be like an M10, and then your next number would be the pitch. And of course, the pitches have to match the male and female, or they won't go together, right? So, all right. So, so the pitch is 1 over the TPI, unless it's metric and you are given the pitch. All right. All right, let's move on. And these 1 starts, 2 starts, 3 starts, and 4 starts mean something to us. It means how far each one of these will travel. In other words, if we did 1 full rotation, 1 360-degree rotation, 360-degree rotation, 1 rotation, how far would it travel from point A to point B? That's called the lead. How far a threaded device will travel, whether it's a nut or a bolt, whether it's male or female, in 1 rotation. That's the lead. Okay? For a 1 start thread, a 1 start, the lead is 1 times the pitch. From now on, I'm just going to use P for pitch. Or it's 1 times 1 over the TPI. And you know how to multiply these fractions by now. If it's a 2 start, in other words, when we cut 1 set of threads and we go to the second, we rotate the spindle on the lathe 180 degrees and start cutting threads again. You're cutting a thread in between the threads. 3rd start, a 3 start thread would be where we rotated a 3rd start, and a 4th is a quarter of the full circle. So a 2 start thread, the lead, how far it travels in 1 rotation, is 2 times the pitch, or 2 times 1 over the TPI. 3 start is 3 times the pitch, or 3 times 1 over the TPI. For start, you got it by now. It's 4 times the pitch. Or it's 4 times 1 over the TPI, because 1 over the TPI is the pitch, right? Okay, all right. Now this matters in certain things. Most valves that you buy, if it's a screw type valve, not a quarter turn full port ball valve, is going to be a 2-start, because they don't want you cranking on a valve handle a lot. The orange juice bottles that we buy from my house, they have a 3-start thread, so it doesn't take much to completely take the cap off the bottle. Because as you can see, a 1-start thread in 1 rotation, it's only 1 times the TPI, or 1 times the pitch. A 2-start's going to do twice that. A 3-start is 3 times that, and a 4-start is 4 times that. So a 4-start thread is a really fast thread. For 1 rotation, it moves 4 times what a 1-start would. Okay? All right. There'll be a simple set of questions on the exam 3. We'll go through that during the review, and you'll see how that works. Now, there's a trick question in there where it'll say if it's a 2-start thread and we rotate it twice, how far will it travel? Well, you start off with 2 times the pitch times 2, right? Because it rotated it twice. Some people catch that. Some people fall trap to it. So, all right. So let's look at another example of a thread. Now this, excuse me, my goodness. This is an internal thread or a female thread or a bee. You know, after a couple of 100 years, I might actually get this down right? Okay, each one of these I've got to do this, start the pin. So this is an internal thread, or it's a B for bore, right? This is an external thread, or A, because the threads are exposed to the air. You can see them without having to peek through the hole. So it's male, this is female, this is an A, this is a B, you know, whatever. This would be a typical 60-degree thread, V thread. They don't all come exactly to a point. They shouldn't. And there's got to be some space in here. So when you get into your actual machining and you start looking in Machinery's Handbook at the threading tables, I used to spend a lot of time on that, but you're not being tested on that, so I'm not going to waste your time right now. You'll see that each one of these has a maximum min. This has a max min. The root has a max min. The pitch diameter has a max min. So you can be within tolerance. And same with the external and internal threading. Now there's got to be some space in here, and this space in here allows these two things to mesh up. And they don't, not all these faces touch. If this is going this direction, then only these faces are going to push. They'll be pushing on the nut, or vice versa. So there's space in there, some gap. And we call that gap backlash. So in a manual machine, if you're sending the carriage or the tool in one direction and you want to reverse and you start cranking on the handle, that handle's going to move some slight amount before the tool or the part starts moving back. That's called backlash. And you have to account for that. You'll learn that in your manual machining class. Or at least I hope you do. That's why you cannot rely on the calibrated handle on a manual machine. You need to watch that DRO or set up dial indicators on your machine. Now here's an example of how some people measure the pitch, and I don't like this, because getting down in here and finding that imaginary point is ludicrous. To me, if you're going to measure the pitch, you really need to be from crest to crest. You'll get a better chance of finding this. But that's really not what you're worried about. You're worried about measuring across the pitch diameter. And we'll see that in a minute. So, you'll see where on the internal, this is B, remember, B. This would be your A thread. All right, external, male, B, internal, female. You'll see that the major diameter is at the root on the female, whereas the major diameter on the male is at the crest. Well, that just makes sense, doesn't it? Of course it does. And then the minor diameter for a male or an external thread is at the root, whereas the minor, smallest diameter in a female is going to be at the crest inside there. And the difference in the spacing of these things is so that they can fit, they can screw in, because they've got to be the same pitch, right? Let's go back. This angle here is a typical 60 degree for a 60 degree V thread. This total angle from face to face is called an included angle. Included angle. Okay? Included angle. Where half of that would be 30 degrees. All right. All right. The rest of this is for engineering. You don't really need to worry about that. Okay, here they show you that on the bottom they've measured pitch from point to point on the crest of the threading. This is a little bit more accurate, I think. Excuse me. My goodness, allergies are killing me. Here's an example of the lead and the pitch. It doesn't matter what the lead is, the pitch is the same. The pitch is the distance between two threads. No matter what, single start or double start, it's still the distance between two threads. The thing with a double start is you got an extra set of threads in here. And here's a triple start, a three start. There's the pitch measure, okay? But you'll see, remember, that the lead for a single start is 1 times the pitch. It equals the pitch for a single start. For a double start, it's twice, 2 times the lead, or 2 times the pitch, I'm sorry. And then for a triple start, it's 3 times the pitch, 3 times the pitch. This is 2 times the pitch. And this is 1 times the pitch. So it equals the pitch for a 1 start. Okay? Now, how do we measure these things? There's 2 ways to measure your threads when you get it done. You could use a gauge. You don't want to use the nut for the bolt. You want to use a certified gauge because there's some tolerances. The easiest thing to do is use, well, it's not the easiest thing. I had to use 3 wires for years because I couldn't afford a thread micrometer. Now I'm old enough and my kids are all gone, so I can afford a good thread micrometer, but I used a 3-wire method. And here's some formulas for a 3-wire method. Your wire sets come with your wires, and there's a formula in each wire set that tells you what the distance over the wires are depending on the thread you're cutting, and you'll get your desired pitch diameter from Machinery's Handbook for the particular size of thread, the number of TPI, and the type of thread, whether it's a 2 or 3 or 1, and what you want to hit. The problem with 3 wires is you need 3 sets of hands. Now, there are some little holders for these things. I used to use Play-Doh and wine corks, and they make little silicone shoes now to fit on the micrometer that hold the wires. But as you can see in this picture here, this individual is having to hold the mic and read the mic and keeping the wires right inside the groove of the thread to use the micrometer to measure that. And with a manual micrometer, not a digital, that even makes it even a little bit more difficult. And then normally you would drop these threads, one of these wires in your machine and try to dig it out. If you lose one of these, you might as well just go replace the set. The 3-wire sets are not that expensive. I think the most expensive ones are around $20. But if you lose one of these wires, throw the whole set away and try not to do it again. Or use Play-Doh to hold the 3 wires together up here at the top, or a wine cork or something like that. Now, Happy Land. This is a thread micrometer. This is a thread micrometer. So it is specifically measured. Here's the spindle. Here's the anvil. Anvil. Spindle. And it's measuring the pitch diameter. So depending on the TPI range, now my set has removable spindles and anvils, so depending on the TPI range, I pick the right spindle and the right anvil, set it in the micrometer, set it to 0, and I measure directly my pitch diameter. Happy days now. No more dropping 3 wires. And I get a direct read. You will have fun in machine shop doing this. Now, we talked about backlash. The distance between the male part and the female part, the A and the B, there has to be some space in there or they won't go together. And how much slop there is changing directions with that screw is it's not an instantaneous deal. It's a backlash. And managing backlash on a manual machine separates the experienced from the wannabe experienced. Now, in CNC machines, those things can hold their tolerances to 5 decimal places or more and do it at light speed and go back and forth. So what do? Well, it's quite simple. They use ball screws. So the female part, this would be the B threads and the A threads, they don't touch each other. What fills up that space are these ball bearings. Now this is a small linear motor. And on big machines, these ball bearings go out, go through an oil bath, a coolant bath, and come back in. So this is what's actually doing the driving. So we saw on one of the other PDFs, you had 2 types of radiuses, right? You had, well, that's nasty. That's a full radius. So the full ball bearing would fit in there. And then you had one that had 2 radiuses. It was more like this, sort of. So the ball bearing would rest on the sides and not fully in contact with the base. Okay? So there are advantages and disadvantages of these. And that's what the mechanical engineers agonize over. But that's how a CNC machine takes care of its backlash. And of course, there will be eventually a time when these things will wear out, no matter how good your lubrication is, and you've got to replace these, and they're very, very expensive. And there are some companies that do aftermarket conversions for manual machines to put ball screws in manual machines, especially your small home shop model mini mills and stuff like that. Here's another picture of a ball screw. This is obviously a light one, just for a small linear motor. You can see how the ball bearings fit inside the entire race and how they fit in here. And these will be lubricated, of course, and to dissipate the heat. Bigger machines, these ball bearings will actually come out and go through a forced oil bath and then back in here. Now that's a better picture of the race. All right. So anyhow, that kind of gives you an overview of the screw and the lead. The important thing for the next exam will be understanding the difference between the relationship, of the pitch and the TPI. It's a very simple problem, as long as you keep your head about you, and should not be a problem. All right. So that's kind of an overview. Like I say, I'm not going to spend a lot of time in Machinery's Handbook because we're not able to go to the lab and actually look at it in person. I could give a whole week-long lecture on threading for different rifle barrels and how you do it. The bottom line is, if you're lucky enough to get a job in a repair shop where every day is something new and different, you'll probably have a female part being brought to you, and you're going to be asked to mate up the male part to it. Well, you could go to Machinery's Handbook and do everything just right, and it still may not fit right because the female may be on the high side or the low side of its tolerance. The simplest thing to do is, if you're tasked with making the male part, you go measure the female part and take some aluminum and start test cutting some plugs and see which fits the best. And then you will get an idea of how you're going to cut your male. So like most things in life, we let the female govern, especially in rifle building. The female part is the action, and so we measure that, and then we cut the barrel shank to fit the action. And that happens a lot in industry too. They'll bring in an old pump, and you're going to rethread a male part to go into the female part, and that's just what you do. So I hope this helps, gives you some idea and some vocabulary between the 3 PDFs that I threw up here. The exam part of threading. Let's see, I think I have the exam notes up here already. Let's see here. There we go. So there'll be a drawing on the exam, and it'll have many different holes, A through, I think, G or something. And we will want, number one, the full threads, and we'll go through this on the deal. The TPI and the distance traveled in one rotation. That would be the lead. So the number of full threads is going to be one of two formulas. Okay. Let's see. Here we go. The number of threads, and we'll go over this again in the video for the review for the exam. The number of threads equals the thread depth, or the length of the thread. So if it's a threaded hole, it'd be the depth, and it'd be times the TPI in the thread. Or it's the thread depth divided by the pitch. Okay? Thread depth divided by the pitch. So if the pitch equals 1 over the TPI, then it's the thread depth divided by the pitch, which is 1 over the TPI. And what do? You're dividing a fraction by a fraction, right? So you turn this upside down. You turn this upside down. Remember, dividing a fraction by a fraction. Oh my gosh. Let me go back to draw. So it's thread depth over 1. So let's say if it's 3/4 of an inch, it's 3/4 divided by this. Then you flip this upside down and then multiply, right? And we're going to turn this upside down and then multiply that times that. So it'd be thread depth times the TPI, which is, what's the pitch? 1 over TPI. So it's still TPI times the thread depth. All right? So we'll go back over this part as we go through it. So let's say we have 3/4 of an inch, and our 3/4 of an inch, we want as many threads as we can get. We want to know the number of threads in that hole. So it'd be 3/4 times, and let's say the pitch is 1 over 24, which means the TPI is 24, right? So that would be 3/4 times 24. So that means we get an even number of 18 threads in that 3/4 inch hole if the TPI is 24 threads per inch. Now, some of these answers would be like maybe 18.8. Well, we don't care about the 0.8. Only in this problem will we never round. Never, 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 never round. Only in this kind of a problem. So the answer would be 18, because we don't care about the 0.8 threads. We only care about the full even number of threads, which would be 18. Again, we will go over this again. And if it was a TPI of 1 over 24 and it's a single start thread, then the distance it travels in one rotation is 1 over 24 of an inch, or the real answer is 0.0 or 0.0416666666666, the number that my ex-wife thinks tattooed on the back of my head, 666. So anyway, that's it for now. I hope this helps, and we will cover this again when we do the review in the next video for exam number 2. All right, we'll see you on the next video.